All right, what's up? My name is Varan Naka, and this is my final presentation for the semester-long research project. My topic is counter-fuzzing, in which I explain the intrinsics of wasting the fuzzer's time with subtle timeout triggers, and that is exactly what I set out to do. For this project, I picked out one of the fuzzing seed ideas, specifically the one about slowing fuzzers down without crashing the program. That's what counter-fuzzing is all about. Instead of trying to stop a fuzzer directly or write totally secure code, we mess with how it works by wasting its time. I picked a program from the official fuzzing benchmark repo, modified with a custom delay logic that's hard to detect, and built a working demo that shows how it slows down under the right conditions. So, with all of that in mind, let's get to it. So, what is fuzzing? Before I talk about what counter-fuzzing is and what I actually did, I want to quickly explain fuzzing in general, just to make sure the foundation is clear. Fuzzing is basically a technique where you throw a ton of random or semi-random inputs at a program and see how it handles them. If the program crashes, hangs, or even behaves weirdly, then the fuzzer logs that input so someone, usually a security researcher or developer, can analyze what went wrong. The key thing about fuzzing is that it's fully automated. A fuzzer doesn't understand your code. It throws inputs at it and monitors behavior like execution time, coverage, or crashes. It's kind of brute force, but a really smart brute force. Fuzzing is a big deal in both academia and the real world. Companies like Google, Microsoft, and security researchers use fuzzers to find vulnerabilities before attackers do. But on the flip side, attackers use fuzzers too, especially when they're trying to find 0 days or stuff to sell in the black market. So basically, fuzzing is a tool that can be used for good or bad. The fact that it's so widely used is why defenses against fuzzing, like what I'm building in this project, are important to explore. The faster and more efficient a fuzzer is, the more code it can test and more bugs it'll find. So even a small slowdown can make a huge difference in the number of inputs a fuzzer can run in a fixed amount of time. That's where this project really starts to make sense. So why counterfuzzing? Now here's where counterfuzzing comes in. Most people, when they think of defending code, think of stuff like input sanitization or firewalls or access controls. And yeah, those are all important, but counterfuzzing is a different kind of defense. It's like defense by deception. Instead of fixing a bug or trying to block the fuzzer outright, we just make it waste time. We let the fuzzer think it's doing something useful, but in reality, it's just burning CPU cycles and garbage. The project's idea from the assignment specifically mentioned two things. First, don't rely on crashes to confuse the fuzzer. Companies don't want to introduce real bugs into production code just to mess with attackers. And second, don't make it obvious. If the fuzzer detects that it's getting stuck, it'll just kill the input and move on. But here's the catch. Fuzzers still use a timeout threshold. So if your program normally takes, let's say, 5 milliseconds to run, but now one specific type of input causes it to run for 2 full seconds, the fuzzer is going to spend way more time processing that one input, even if it doesn't crash the program. That means you've just slowed down the entire fuzzing campaign. You've essentially wasted the attacker's time, or at least severely limited their ability to explore more of the program. That's the value of counterfuzzing. It's not about being bulletproof, it's about being annoying. And for defenders, that can sometimes be enough to shift the balance. So here's what the assignment actually asked us to do. The seed project I picked was under the fuzzing category, specifically the counter-fuzzing one, and the write-up was pretty clear about what the goal was. First, I had to pick one of the programs from this benchmark repository called Forte Fuzz Bench. These are real-world fuzzable open source projects that are commonly used to test fuzzing techniques. Then I had to modify the code to include what they called timeout inducing code sequences. In other words, I had to insert logic that would cause the program to slow down under the right conditions, but it had to be subtle. The point wasn't just to add a big while true loop somewhere obvious, it had to be creative. And this part was important. The more creative, less detectable, and more automatically insertable my code was, the better the grade. So I knew from the start that I couldn't just hard code a delay when the input starts with an S or something easy to pattern match. I had to bury it inside real looking logic. Finally, I had to prove that it works by running a demo. So that's what I set out to build. A working example of counterfuzzing that looks like a legit logic but wastes a ton of time under the right conditions, while passing all other inputs as normal. So the program I chose to modify was called CJSON, which is super lightweight JSON parser written in C. It's actually a pretty popular library. I've seen it used in multiple embedded systems and low-level tools that need something fast and simple to handle JSON. It was also one of the programs included in the Forte Fuzzbench repo, which made it fair game for the project. What made it perfect for counterfuzzing is it already had this small main function inside its fuzzing folder that reads a file, parses it with CJSON parse, and optionally prints the result. That meant I didn't need to go digging through a bunch of source files. I had a clear entry point where I knew the fuzzer would be interacting with the program. So my plan was this. I would take the main function and inject delay logic in a way that doesn't break anything or cause a crash. The goal was to make the program behave totally normally for most inputs, but for one very specific kind of input, one that I chose, the program would enter a logic bomb that just wastes a ton of time. The cool thing about using CJSON is it also takes a file input, so I didn't need a full fuzzer sub just to test it. I could just echo test strings into files and run it manually to see the effects, measure the time, and verify whether the delay was happening. So, with all that in place, the program picked the objective defined. I started thinking about how to actually build the slowdown logic and hide it from both the fuzzers and humans. All right, so let's talk about where I actually inserted the delay. Like I mentioned before, the CJSON program has this nice compact main function inside the fuzzing folder. It does exactly what you'd expect. It takes a file as input, reads the content into memory, then passes it into CJSON parse to parse it. That makes this the perfect entry point for fuzzing. In a fuzzing scenario, the fuzzer would generate all sorts of random JSON or malformed data and feed it to this function through the file interface. The program just reads whatever is in the file and tries to parse it. So I didn't need to go dig into the internal parsing functions or mess with the library itself. All the fuzzable behavior is already exposed right here. And because this function runs on every input, I knew this was the exact place I want to inject my slowdown logic. If I had put the delay too deep inside the parsing logic, it might not have gotten triggered on every input, or I'd risk breaking the program. But by putting it right after the file is read, I had full control. I could hash the entire file content, check for a specific condition, and delay only when the condition is met. The key part here is that this delay had to run before the actual parsing, so that I'm slowing down fuzzers no matter what kind of JSON they send. Even if the parsing fails later, they still waste time on the delay. That gives me a consistent slowdown path without introducing instability. Now, before I show you the solution I actually went with, I want to go over a really basic version of counterfuzzing, just to explain why it's not good enough. A very straightforward idea would be something like check the first byte of the input, and if it's specific value like s, run a giant while loop, like if JSON 0 equals s, while I is less than 1 million I++, something like that. This works technically. The delay fires, it slows the program down for that input, but the problem is it's way too obvious. Both static analysis tools and coverage guide fuzzers can figure out that this condition leads to a heavy computation path. The condition is just way too simple. A smart fuzzer will either detect the pattern and discard the input or keep hitting it and adjust its mutation strategy just to avoid the branch entirely. Either way, your delay is not effective long term. Also, a human reverse engineering your binary would spot that logic bomb instantly. It's sitting right there. Oh, input starts with S, run a giant loop. That's not suspicious at all. And like the assignment said, the more detectable and less creative your code is, the lower your grade. So this kind of trigger doesn't cut it. I had to come up with something way smarter, something that looks like normal code, doesn't stand out, and is hard to reverse engineer even if you know what to look for. So this was my smarter approach. Here's what I came up with instead. And this is the centerpiece of the whole project. A hash-based trigger using the DJB2 hashing algorithm in a weird-looking but legit mathematical condition. What I did was take the input file content and run it through a DJB2 style hash. That's a classic hash function that shifts and adds each byte in the string to get a final hash value. Then, instead of just checking for a specific character, I created a condition that looks like this. If hash and then the hash divided by 113 equals 42. That looks totally arbitrary to anyone reading the code. If anyone sees it, they'd have no idea what input causes that condition to be true without Bruce forcing it. So now, instead of the slowdown being tied to something obvious, it's based on the hash of the entire input string. That means I can pick any JSON looking input, find one that matches the condition using a Python script I wrote, and that input will trigger the delay. It's way harder for fuzzers to figure out this logic. From the fuzzer's perspective, it's just a slightly longer execution time. But because the hash function and the condition are non-trivial, there's no easy way to predict which mutation will cause a delay again. And that's exactly what the assignment wanted. Something subtle, hard to detect, and reusable. I even wrapped the logic into a macro, which makes it easy to drop into other programs later if I want to expand the project. So I want to take a second and walk through the actual goals I had for this logic bomb and how I hit each one with this design. First goal, make it hard to detect. I didn't want a fuzzer or static analyzer to look at the code and go, oh look, an infinite loop tied to a character check. By using a DJB2 hash and a bitwise modulo condition, the code looks a lot more something a legit developer might write, maybe for validating some unique identifier or checking a hash collision. Second, make it automatically insertable. I wrote the whole thing as a macro called counter fuzz delay, which I can call like a function but expands inline. It's self-contained, doesn't require external headers, and doesn't rely on modifying other parts of the code. That means it's portable. If I want to drop it into a libjpeg or bin utils or some other benchmark in the repo, I could do that in one line. Third, make it look normal. The loop inside the delay isn't written like while true, which would be a red flag. Instead, I use a volatile counter and a loop that looks like a performance test or maybe even a warm-up loop. And it exits cleanly. There's no crash or error, just a long pause and then normal behavior. And lastly, make it effective. The delay loop I wrote lasts about 2 seconds of execution time when it's triggered. That's a huge amount of time in fuzzing terms. If a fuzzer has to wait 2 seconds for every input that hits this condition, that's a massive slowdown. Okay, so here's the actual code for the macro so you can see what's going on. It starts by using the hash to 5381, which is standard for DJB2. Then it loops through every byte of the input buffer and updates the hash. That part is straightforward. It's a simple shifting and adding function, but it spreads out the values nicely across the hash space. Then comes the interesting part. I take the final hash, Azor, take it with ZX dead beef, which is just a fun hexadecimal constant, and then mod it with by 113. If the result is 42, the logic bomb triggers. That's it. If the input doesn't match the hash condition, nothing happens. The program continues as normal, but if the condition does hit it, it prints a debug message, which I only added for the demo purposes, and then enters a loop that wastes about 2 seconds. That loop uses a volatile counter to make sure the compiler doesn't optimize it away. It runs a few billion iterations just to waste time, but it doesn't affect memory or logic or output, so it's totally safe. And again, this macro can go anywhere in the code. I dropped it right after the input is read, so it always runs. But if I want to make it more surgical, I could put around certain code paths or only trigger on larger inputs. It's completely flexible. So that's a logic that powers the whole counterfuzzing setup. And now I'll show you how I generate inputs that actually cause this to fire. So here's the thing. Once I wrote the macro and put the delay logic in the program, I needed a way to actually test that it is working. And that's not easy to do by hand because I'm not just looking for a specific string. I'm looking for an input that hashes to a very specific value using that DJB2 function. So instead of guessing or brute forcing random inputs manually, I wrote a Python script to do it for me. The idea was simple. Take a known prefix like trigger, then loop over a bunch of possible character combinations, and for each one, calculate a hash using the exact same logic as my C code. If the final condition, which is the hash 0x deadbeef mod 113 equals 42, passes, then we found a trigger input. I kept the characters set small and the suffix length reasonable. I wasn't trying to brute force the whole universe, just find something that worked. The script outputs the valid input and writes it directly into a file called slow.json. That's the input I used in my demo to prove that the slowdown triggers. The nice thing is I can regenerate a new slow input anytime I want just by rerunning the script, so it's repeatable. If I were building a fuzzing defense across multiple programs, I could actually generate a whole list of inputs that hit the bomb and scatter them throughout my test cases to slow down different paths. The script also helps prove that the logic bomb isn't tied to a single hard-coded input. I can hit the delay from multiple valid inputs, and that makes it even harder for a fuzzer to avoid once it starts encountering them. One problem I ran into early on was figuring out whether the logic bomb was actually firing. Like, yeah, I had the code in there, but when I ran the program, it finished so fast that I wasn't even sure the delay was being triggered. So I added a couple of debug lines to print out the hash and show whether the condition passed. Specifically, I printed a final hash value, and then right before the delay loop, I added a message that said a warning symbol and then delay triggered with the exact hash that caused it. This gave me full visibility. If the input didn't match the hash condition, I'd see a normal message and the program would finish it under 5 milliseconds. But if the hash condition passed, I'd get the debug output and then I'd watch the program hang for a full 2 seconds. I also use this debug output to cross-check against the Python script. So whenever the script told me this input should trigger the delay, I drop it into a file, run the program, and verify the hash is matched, and that the delay actually occurred. And it wasn't just for debugging either. I kept these messages in for the final demo so I could show step by step that the condition was being hit and that the delay wasn't random. It's tied to a specific logic path that only fires when the input is crafted exactly right. So between the debug print and the Python script, I had full control over the entire system, from input generation to trigger verification. It let me tune the delay, verify correctness, and set up the demo you'll see next. All right, let's start with the fast path. I created a basic test file called fast.json, which just contains a normal input like fast input. There's nothing special about this one, no weird characters, no magic strings, just regular JSON that parses fine. When I run the program with this file, the counter fuzz delay macro still runs, but the hash condition doesn't pass, so no delay is triggered. You'll see in the output that it shows the hash, says nothing about delay, and the total runtime is about 4 milliseconds. This acts as our baseline. This is what a normal input looks like. It proves that my logic bomb doesn't impact regular execution. If you ran million normal inputs through this program, they'd all finish super fast because the hash check doesn't pass. And this is really important. If the delay happened too often or randomly, it'd be obvious to fuzzers or users that something weird is going on. But because it's so specific, this fast path runs clean and fast almost every time, just like you'd expect from a normal JSON parser. Now for the slow input. Let's look at what happens when we feed in the slow input, the one the Python script found. In this case, the input looks something like trigger and then I. And the exact string gets hashed, and it just so happens that it passes the bomb condition, the result of hash deadbeef mod 113 equals 42. When I run the program with this file, you can see the debug output kicks in. It prints out the hash and says warning, delay triggered. And then the program takes about 2 full seconds to finish. That's a massive slowdown compared to the fast input. And again, there's no crash. The program works just fine. It parses the input and exits cleanly. It just burns time on the way out. That's exactly what makes this perfect counter fuzzing strategy. A fuzzer hitting this path is going to waste time here, and the more input that falls into this trap, the more time the fuzzer wastes. That means it explores fewer paths, finds fewer bugs, and ultimately becomes a lot less effective. And from the outside, it looks totally legit. There's no stack trace, no segfault, no error messages, just slow execution on a specific, hard to replicate input. That's the sweet spot for this kind of defense. All right, so now I'm going to run the demo script that compares the fast input and the slow input side by side. You'll see both outputs one after the other. Starting with the fast input, this is just a regular JSON file, nothing special. The hash value gets printed, and you can see that doesn't match the trigger condition. So the program will run normally with no delay and finishes about 4 milliseconds. So let me real quick pull these up so that you can see. Nope. So in my terminal, real quick, I wanted to first show you, because I'm running a script called demo. And in the demo script, you can see the fast JSON only has echoed in fast and input as the conditions. And then for the slow.json that will be used, it's actually using a Python script that finds an actual trigger condition that is met and put it in the slow JSON. And as you can see here, this is my Python script that I made. And this is what actually finds the trigger condition that needs to be met and then puts it into the slow.json file. So as you can see here, again, this is the demo. And then I will actually demo it here for you. So demo. So now you can see the fast and the slow right after. This is the slow input on the bottom. This is one of the crafted inputs that my Python script found. It hashes to the exact value that hits a trigger condition. And right there, you can see the warning delay triggered message. That means the logic bomb was hit. And we burn about 2 full seconds inside the fake loop. And just like that, same file format, clean input, no crash, but completely different behavior under the hood. This is exactly what makes it dangerous for fuzzers. They'll waste tons of time trying to figure out what's going on without getting any closer to a real bug. So this right here is the core of the counter fuzzing idea. Make one tiny input slow everything down and never raise any alarms. So here is the actual C.json file that I edited. That's from the Forte repo bench. And here is the macro that I created for the counter fuzz delay. This is what triggers the warning that you will see in the console. And then as you can see, I put it right after the red file, this print input. And this is where the hash and everything actually triggers. And you'll actually see on the console that because of this, which looks like a normal set of code, will actually trigger the delay in time because of the macro that's inserted here. And now moving on. So now here's a side-by-side comparison of the fast input and the slow input just to make it really clear how big the difference is. The fast input finishes about 4 milliseconds. That's exactly what you expect from a simple JSON parser running on a small file. That's also how the program performs for 99.9% of all other inputs. But the slow input, that one takes over 2 seconds. And again, it doesn't crash or fail, it just burns time quietly. That's over 500 times slower than normal. And that's just for one input. If a fuzzer keeps mutating from this base input and keeps triggering similar hashes, it could waste minutes or even hours during a campaign, all while learning nothing useful. That's the kind of slowdown that makes the fuzzers miss coverage goals, skip inputs, or throw away crash test cases just because the fuzzer's internal clock ran out. So, this isn't just a neat trick, it's a serious disruption tactic. And when combined with more advanced fuzzing setups, this kind of slowdown can completely derail a fuzzer's progress. All right, now let's take a step back and look at this project through the lens of the actual assignment goals. Did I hit all the points that were required? I'd say yes, and here's how. First, I did exactly what the assignment asked by choosing one of the programs for the Forte Fuzzbench repository. I picked CJSON, and this is a real-world JSON parsing library that's already known to be fuzzable. Second, I added a timeout-inducing code sequence to it, but not just any delay. I added a delay that's creative, hard to detect, and tied to logic that looks totally legit. I didn't just write a while loop and call it a day. I built a full hashing and condition checking system that only triggers under very specific circumstances. Third, the assignment emphasized creativity and subtlety. I think this is where the project really shines. My delay logic uses a DGB2 style hash function, bitwise math, and seemingly random condition that doesn't look malicious at all. On top of that, I wrapped it into a macro that could easily be reusable or dropped into other projects, which adds that automatically insertable factor that they're looking for. Fourth, I actually proved that it worked. I wrote my own input finding script, validated the behavior using debug messages and hash values, and demonstrated the delay both in a fast path run and a slow path run. You can see with your own eyes the logic bomb does trigger and that it wastes real time. So from top to bottom, I modified the right program, added the right kind of logic, made it subtle and effective, and demonstrated that it works. That checks every box, I think. Now, let me be real. Even though this product worked and hit the goals, there's definitely some ways it could be improved or expanded if I had more time. For one, the logic bomb right now is in a single place, right after the file input is read. That's fine for this demo, but in a real world application, I could scatter these checks throughout the different code paths, and maybe tie different delay triggers to different parts of the input structure, or even make the delay scale based on hash results. That would make it way harder for a fuzzer to predict or work around. I could also randomize the condition itself. Like, instead of always checking for the value 42, maybe I have a secret key that changes the trigger threshold every time the program is rebuilt. That would stop the attackers from reverse engineering the trigger once and reusing it across the systems. Another idea is adding multiple tiers of delay. Maybe mild slowdowns for low probability matches and longer delays for higher confidence triggers. That kind of variability makes it even harder to optimize fuzzing runs. And finally, I could expand this approach beyond just CJSON. Since my delay logic is macro-based and self-contained, I could take this exact same idea and apply it to other programs in the fuzzbench repo, like libjpeg or binutils, and see how much it disrupts fuzzing across a broader set of targets. So yeah, the project is complete, but there's definitely more room to grow this if I ever want to take it further. To wrap this all up, this project was about counter fuzzing. My goal from day one was to build something subtle, smart, and effective at slowing down fuzzers without crashing or obviously breaking the program. I picked CJSON because it's small, clean, and easy to test, and then I built a delay mechanism that triggers only on very specific hash-based inputs. It wastes over 2 seconds of execution time when hit, which in fuzzing terms is a serious hit to efficiency. I verified it using a custom Python script, debug outputs in the program, and live demos showing how fast and slow inputs behave differently. And the whole logic is wrapped in a macro, which means it's portable and ready to be dropped into other programs later. Most importantly, this matches everything their assignment asked for. It's creative, subtle, and hard to detect, and proves a logic bomb can be a viable strategy to waste fuzzers' time without doing any real harm. So yeah, that's my counterfuzzing project. I appreciate you all for listening, and if anyone has any questions or wants to see the code in more detail, I'd be happy to walk through it in the comments. So that's everything I had for the project. Again, thanks for watching and following along. If you have any questions about how to implement the delay and how the hashing works, or even how the macro could be adapted for other targets, feel free to ask. I had a lot of fun with this project, especially getting the delay to hit exactly right. I'm glad I got to show it all here. So again, thank you.